It's a great pleasure to have Professor Amy Zhang give the talk today. She's been at UT, for I think a couple years now, maybe a little bit, two and a half years. Yeah, she did her PhD from McGill, postdoc at Berkeley, and she also used to be at FAIR in Meta. And she works on RL, many different RL things. So we'll talk about some of them today.
Wasn't she a founder of the RL conference?
RL conference, yeah.
In fact, you founded that.
Yes, with a group of people. It was not just me, but yes, we created an RL conference because we noticed that RL was disappearing from the major machine learning conferences. The major machine learning conferences are just too large, and so it was nice to have our own smaller community. So all of you should definitely attend if you're interested in RL. RLC is a fantastic venue.
Do you want the lights on or off?
Whatever.
This is off.
Oh, that looks nice.
Yeah.
Off. Let's do that. Okay. All right. So yeah. So today I'm going to talk about RL. I'm going to talk about successor measures and self-supervised RL. And so let's first start, with our motivation. Like so many other talks these days, I'm going to talk about scale, right? The motivation is that we now have access to these large scale video language data sets of humans performing diverse tasks. We've now also have collected large scale robotics data sets. So, 1 million plus real robot trajectories. And the question that we want to ask is, how can we leverage all of this data for downstream control tasks? And we have another question, which is, how can we front load training policies to improve downstream performance? Right. So we want to borrow from the success of large language models, of foundation models that have this huge initial pre-training procedure when you don't know what your task is yet. Right. We just have some kind of self-supervised learning objective. And then downstream, we just use context in order to zero-shot extract what is the best policy for language models to output for us the language that we want to see, right? And so we want to borrow from this success and think about how can we do this for RL? And so, one possible application of this is robotics, is how can we train general robot agents using video data from humans or from these large-scale offline robotics data sets. But we can also use these ideas to train large language models or video generation models, right? Because all of these sequential generative models we can also think of as RL problems. Okay, so just a roadmap. Inspired by the success of foundation models, how do we apply these ideas to RL? And so we have this work called proto-successor measure with Peter and Siddhant, which is a form of behavioral foundation model that does this type of self-supervised pre-training on offline data, and we can zero-shot extract policies for some downstream tasks. So I'll talk a little bit about that. I want to also show what you can do with this kind of BFM. And one thing is that we can actually extend this zero-shot policy extraction and combine this with a VLM or with language or video in order to get zero-shot language conditioned or video conditioned policies. So we'll see some nice videos of that. And then we want to try and simplify these objectives. So this maybe doesn't make too much sense right now, but in order to learn these behavioral foundation models, we have to use RL. We're using temporal difference learning. And so we want to say, can we simplify this further? Do we actually need temporal difference learning, or can we just use a more myopic, like one-step objective? And so it turns out regularized latent dynamics prediction is a strong baseline for behavioral foundation models. And then I want to tie this into a lot of other ideas in self-supervised RL, right? Self-supervised RL is not a new concept. There's a lot of different ideas stemming from different perspectives that give rise to different methods. But it turns out that all of these methods can be tied together using this idea of a successor measure. And so I want to show how these things all tie together. So if I think about what is a simple example of a self-supervised RL method, and here self-supervision just means that I'm assuming I don't have access to a reward, right? I have an environment or I have an offline data set of transitions, but I don't have reward. So goal-conditioned RL is one of the canonical examples of self-supervised RL, right? Where an agent is being trained to solve a number of tasks within the same environment. And so we're just trying to reach different goal states in this environment. So a goal is being sampled at the beginning of the episode. Even though this is self-supervised RL, where there is no reward being given by the environment, I'm still defining an automatic reward for the goal condition setting. And so it just looks something like this, right? So I have some sparse reward where I get a reward for reaching my goal and no reward otherwise. And then I can get fast policy inference for goal condition tasks, because I'm assuming that I've trained some goal condition policy, so I can just pass in some new goal, maybe an unseen goal, to my policy, and it will give me some sequence of actions to take to try and reach that goal. So this works great, but the problem is that if my task can't be defined by a goal state, I can't use this, right? This only works for state goals. So let's try to generalize this idea to arbitrary tasks. And one way in which we can do this is by defining the successor measure. So this is a measure over future states visited, and you can just see that this is basically an expectation over the discounted probability of me visiting some sequence of future states. This is the discounted measure of ending up in some future state, right? And the most common form of this can be denoted as this. So it's some measure M, condition on a specific policy, and I'm starting out at this state action, and this is the probability that I will end up in S plus. Okay. And so why do we care about this concept, about this M? It turns out that we can extract the optimal policy very easily by just computing the argmax over M pi times some reward, right? So M depends on a policy, but it does not require any information about a reward. So I can have some reward at test time. As long as I see some reward at test time, I multiply it to this occupancy measure and I get a Q function, and I take the argmax of that and I can get the optimal policy. So the nice thing about the successor measure is that it gives us a reward independent representation. We have this nice linear objective for policy optimization. And so we can design some framework of a unified objective that says, okay, now I can start to design a training framework where I have a reward-free phase, where I just need to learn M pi for arbitrary policies. And then now, once I'm provided reward at test time, I can extract my optimal policy. Okay, so this sounds maybe too good to be true. Unfortunately, we have an infinite number of policies to compute the successor measure for, and so this is intractable. How do we actually characterize all of these possible policies, or maybe the set of policies that we actually care about? And we know that if we think about goal condition RL within this framework, we see that goal condition RL is actually limiting the space of policies that we're considering. We're only considering policies that can reach specific state goals.
Amy?
Yes.
Sorry, I have a stupid question.
Yeah.
So at training time, there's no reward, right?
Yes.
But how do you use reward at test time? I missed that.
So it's just according to this equation, right? So if I'm seeing reward at test time, I'm like in this example.
Okay, so I still am maximizing reward at test.
At test time. So
second phase, the reward-based phase.
Right.
in this phase, right? So I'm learning this successor measure for arbitrary policies. So I haven't talked about how I get these policies, but let's say I have a bunch of policies. I'm learning M. There's no dependence on reward. At test time, as I'm interacting with my environment, say I'm receiving reward from the environment based on the states that I'm visiting.
So is the analogy here like I can do unsupervised learning, self-supervised learning during training for like standard deep learning, and then at test time, and then I can do some fine tuning and do like supervised fine tuning the rest of them when I actually have some like
Yes.
labels or.
Yes, so I'm saying zero shot, and Peter, I'm sure, is wincing at me saying zero shot constantly. But yes, you are doing some fine tuning, but the point is that we don't need to fine tune the whole model, right? Like we don't need to fine tune the entire policies. We don't need to fine tune this M. We just need to okay, it's not on this slide, but we just need to learn some small thing that allows us to extract the
let me-
optimal policy for a reward.
Let me try maybe. So you actually said something that was a little bit imprecise, I think. You said that the successor measure is the probability of ending up in S plus. But really think of the successor measure of if you execute policy pi, what percentage of the time will you spend in each state?
Okay.
Right? And so if you know that for every policy, now you have a reward function that says these states give you reward and those don't, you can then just say the policy that lands me in these states the most is the one I want.
Yeah.
So, a quick follow-up. Then why does it have three arguments, S, A, and S plus? Shouldn't that just be have a single argument, which is the state?
It depends on where you started out,
Or
right? So this
starting state,
essay,
starting-
where I am right
starting
now.
action and
And
then
then-
the long-term.
Yes, the
Yeah.
long-term probability of the amount of time that I will spend in S.
If you follow policy pi forevermore.
Okay,
Yes.
so the reward free phase is in some, like if this was like Markov process, then the reward phase is like learning the probability distribution and how to control it. But not really
Yes.
thinking about any
Yeah.
downstream.
It's
Yes,
just how the world works. It's the
It's just how
dynamics.
the world works.
It's how do if I'm in this policy, which states will I get to most? And then later you're gonna tell me which states are good, and I'm gonna pick the policy that goes to those good states.
Yeah, that's all.
right. And so because this gives me the probability of how much time I spend in every state, right? In every state, I just have to multiply that with the reward I get for that state. And this gives me my Q function, right? And then I just need to do argmax according to that Q function in order to get my policy. And so because I can get this Q function, I can get zero shot in the sense that I just have to multiply the reward that I see with this quantity that I already have. And then, if I have, as an example, if I just have like a one-step dynamics model, right, then I can just sample lots of actions and then pick the best one and take that action. And so that would be an example of a zero shot policy extraction at test time. Okay. So we have, so proto-successor measure is one way in which we can learn this successor measure at training time. And so we do this with a very specific breakdown of the successor measure. And the observation that we rely on is the fact that the Bellman equations are affine. So here I just have the Bellman equation written for a visitation distribution under some specific policy. But this Bellman equation I can also write for successor measures. And so because this Bellman equation is affine, it means that there exists a hyperplane of all possible successor measures subject to the constraint that my successor measure, it's a probability, so it has to be greater than or equal to 0. And so I can represent this hyperplane using a basis set phi. And so every set of weights for those basis vectors and a bias term corresponds to a specific successor measure, which means it corresponds to a specific policy. So the space of all possible policies for my MVP lives on this hyperplane. So if I can just learn phi, if I can learn this basis set, then I have a closed form solution to compute the successor measure for any policy. Okay. So this means that I can just represent my successor measure as phi w plus phi. And now I just have to learn these components. And for any given reward function, I just need to solve this linear program on W. I just have to learn what the weights are that will maximize that reward. And so my loss function for learning the successor measure is equivalent to TD learning. It's just TD learning with my successor measure instead of a Q function. And my successor measure is now parameterized by phi W and B. And I need to minimize this for all possible policies. And so in practice, the way that I do this is I use a discrete codebook to represent those policies. And this discrete codebook gives me a way to uniformly sample different policies during training time in order to learn the successor measure.
Amy, there's a question.
Yeah,
Don't you? No. Oh, you know.
okay. So this gives me a representation that's not dependent on policy. And so it's a truly universal representation. Okay. So this allows for simple inference on any reward function. I can get zero shot, quote unquote, extraction of near optimal policy. So it's near optimal in practice because this is a learning objective. And so everything is now approximate. This is ideal for environments where reward is not known. So I'm assuming that I have a setting where I don't have my reward, or I have cheap computation during this pre-training time where I have access to our algorithm is designed for the case where I have a full coverage offline data set. But there are versions of this that exist, or you can design this for the setting where you have online access to some environment before you know what the reward is. And so this is a behavioral foundation model. All right, so let's look at some results. So let's just start it with some simple grid world examples, because we can visualize the successor measure. We can visualize these Q functions more easily. And so in this grid world example, G here denotes the goal. And so this is the Q function. This heat map represents the Q function extracted from PSM. So this is zero shot in the sense that PSM is being trained on this grid world environment before this goal is known. And then I'm going to compare against a couple of other baselines, right? So first I have FB, so forward backward learns both the optimal policy and state features jointly for all reward that are in the linear span of state features. This FB method is pretty similar. It's a slightly different parameterization of the successor measure compared to PSM, I think is the main thing to note right now. And then Laplace, this is just Laplacian features, which are learning features of a state by considering the eigenvectors of the graph Laplacian representing the transition matrix of the MDP. And so this is learning the spectral basis rather than the basis of the successor measure of the MDP. And so the main thing that I want to note is that PSM is more sharply concentrated on the optimal state action pairs, right? So we can see that there's more variation of the value over the entire grid world space. And so then you can't see these probably, but there are green arrows basically representing the argmax over all actions of the Q function that I extract with each of these different methods. And so we see that PSM also has more correct optimal actions, more correct actions compared to FB and Laplace. Yeah.
Can you say something about what the policy codebook looks like here?
So we're basically we're the problem with this method is that we have to consider all possible policies. We have no information telling us what is the space of policies that we actually care about downstream. So we have to define some latent space that we're sampling from to represent this space of policies by using a discrete code book. And so this is just it's a way for us to create like a discrete latent space. It means that we can now sample uniformly over discrete space a lot more easily than over a continuous space. Does that is there any?
So I'm wondering if there's like some specific structure here, right? That you is a general construction that you can use the same code book for any task. So if I wanted to, I don't know, use your technique for robot, motion planning and 7 degrees of freedom with kinematics, right? Would you use the same policy codebook, or would you use something else?
The policy codebook is dependent on the environment, which means you're dependent on the state action space. So it wouldn't transfer across different environments.
The codebook is really just a set of slots, right? It's not like there's nothing pre-compiled about the structure of the codebook. It's just sort of a discretization that compresses the representation into some sort of fixed latent space, but there's nothing predetermined about it.
Yeah.
So, if I understand correctly, the PSM is just trying to model the world and call it distribution. So what does an optimal state actually mean? Because we are not actually trying to maximize any code.
In this example,
Yeah,
in this example, we are specifying a goal. So that's how we can evaluate the quality of the successor measure being
this
learned.
is not how it's this is evaluating.
This is
This is
evaluation.
evaluating how it works in this zero shots.
Yes, yeah.
But-
So,
Yeah.
yeah. So we're multiplying the successor measure with a reward denoted by this goal. And that's how, and so what I'm visualizing here is the Q function, not the successor measure.
Okay.
Yeah. Any other questions? Okay. Okay, and so we just have some scaled up experiments as well on point mass, quadruped, cheetah, and walker. And I'm just gonna walk through some of these additional baselines that we have. So we already saw what Laplace was. FDM is just features learned through one step forward model predictability. SVD is the singular value decomposition of the successor representation. We already saw FB. HELP is just a variation of FB that's pre-trained using goal reaching. And the method that they use to learn the successor measure is just a slightly different offline RL method. And so we can see that PSM overall performs consistently better than all of these other self-supervised approaches, or about on par for some of the environments. And so we just have several tasks that we define for each of these environments. Okay, so now let's look at how we can take this behavioral foundation model idea and use it to get language condition policies. So in order to incorporate language into this zero-shot RL framework, we have a three-step process. The first is imagine. So we're going to use a fine-tuned VLM. So we're going to assume that we have some language command that we want to get a policy for. We're going to pass that into a VLM and generate a video trajectory representing that language command. We're then going to project, so we're going to map from those generated observations to states in our target domain. And in practice, we do this using nearest neighbors in some learned latent representation space. And then in the third step is where we actually use our BFM. So we're going to now extract a policy to match that demonstration, right? So from the projection step, we now have a non-ordered set of states in our target domain. So some occupancy. You can assign reward to those states and use that to extract a policy from our BFM. And so here are just some examples. So if I have very simple language commands like cartwheel or crawl like a worm or bunny hop or jump high, I can use a behavioral foundation model and extract these policies that correspond to these language commands. So I can also do this without requiring a VLM, right? So in this case, let's assume that instead I can just use a real video or demonstration. So here I'm just taking some YouTube videos of various poses. And so then I can just do the project and imitate steps. I'll just project from these real video frames to my target domain. Again, assuming that I have a good latent representation that aligns these well, and I can extract these policies. Okay. So that's just a simple demonstration of what's possible with BFMs.
Amy, how do you explain, so the unordered aspect of it? So in a
Yeah.
lot of skills, the order matters. So why do you think this works for us without the ordering constraint?
So I mean, so technically the optimal policy for a task as defined by a stationary reward function is unordered, right? The states that I assign reward, I can't assign a specific target ordering to those states, right? So in the standard RL formulation, I can't assign an ordering to states for an optimal policy. But actually in practice, technically, there is an ordering here. Because if I go back to that definition of the successor measure, and if I also think about how Q functions are defined in RL, usually I have a discount factor. Let me go back one more, right? I have this discount factor gamma. And so if this discount factor is less than 1, then technically I am imposing an implicit ordering over my states. I'm saying that I would like to achieve rewards sooner rather than later. And so that imposes an ordering over my states. But like generally, I think things are designed to be unordered. But do you have a specific?
I mean, if there were a policy that created the same states as a lunge, but in a scrambled order,
Mhm.
technically, it would like that policy would be just as preferred.
Yes.
And so it has to be that we think that there's no, that it's unlikely that there is such a policy, that there's something about these skills that makes it that you have to do in this order to visit these states. But that's not.
No, yeah.
It's not always the case.
No, that's not always the case, right? And so I can scramble. But again, I think that's the problem with the RL formulation in general, right? Which is that like I can scramble some set of states in a demonstration. And according to, like an RL method learning from demonstrations, any ordering of those observations is the optimal policy.
So if I want to do a cartwheel to the right, but it's symmetric, so it could, easily just do a cartwheel to the left, right? Then it would get the reward, even though it's
Yep.
not what I wanted.
Yes. Yeah. And there's not really any way around that other than if you use a discount factor. If you use a discount factor, then I am now saying that right, like the first frame has higher reward than the last frame, and that now imposes an ordering of iframes. So that's I think the way around that in practice. Okay, so we'd like to understand if we can simplify this objective further for learning this representation that captures this successor measure or a notion of future occupancy about policies, right? So the question that we wanted to ask is, do we actually need TD learning, right? We're capturing future occupancy for all possible policies. Really, in some sense, all we're really capturing is information about the dynamics of the environment. And so this was more of an empirical exploration, but the question was, is a latent dynamics model plus some feature diversification in order to prevent collapse, is this and so in practice, we use orthonormal regularization. And so let's just define the components that we need here. So we need a state encoder. We need a state action encoder. And we're going to impose some additional structure, which is that we want our latent dynamics to be linear with respect to this state and state action representation. All right. So our representation learning objective is just this latent dynamics model objective. So given some trajectory, I'm going to encode my first state into my latent representation space. I am going to predict future latent states according to my linear dynamics model. And then my loss is just making sure that the output of my dynamics model matches the encoded actual future state. So the problem, if we just look at this objective, maybe you're thinking, well, if I learned a latent representation that just collapsed all states to the same point in my latent representation space, then my dynamics loss is automatically going to be, it's very easy for me to minimize this loss and have it be 0, right? Because I just have to predict that same point in my latent representation space. So in order to prevent this collapse, then we also incorporate this orthonormal regularization to enforce that all of my states have to lie on a hypersphere. And so once I use this combination of these two objectives in order to learn my latent representation, I can freeze that and then learn my successor measure on top of that through Psi. So it turns out that this this very simple objective, RLDP, is competitive to PSM, to FB, HELP, and these other kind of self-supervised methods for learning behavioral foundation models, which is quite nice. So another nice thing about decoupling learning policies from learning this representation is that it means that RLDP works with partial coverage data sets. Right, so if I think about all of these other prior methods are assuming access to a full coverage data set. And we need this because we're learning policies in order to learn the successor measure. So, and in practice, if I tried to learn a policy from some offline data set, it's very easy for me to extrapolate beyond the support of my data set, and things can go very wrong. But because RLDP is predefining this representation, just using one-step dynamics of the support of my data set of transitions, it means that it can handle partial coverage a lot more gracefully. And so we see that in practice, that RLDP is able to achieve better performance in partial coverage settings. Okay, so how does all of this relate to other ideas in self-supervised RL? And so now I'm going to introduce like other perspectives from self-supervised RL and connect all of them to successor measure. So we've already seen goal conditioned reinforcement learning. In goal conditioned RL, we're learning a goal conditioned Q function. And it should be pretty obvious to all of us now that the Q function is going to be proportional to my successor measure. And so that's the connection between goal conditioned RL and successor measure. There's another type of self-supervised RL objective called mutual information skill learning. And so this family of algorithms tries to maximize mutual information between states and skills that are represented by this latent space Z, or between transitions and skills. And so these missile methods rely on lower bound that require training this variational distribution. And it turns out that I can extract the successor measure using that learned variational distribution. And then I can now perform policy inference by searching through the space of skills. And I'll talk a little bit about why this is potentially suboptimal. There's another broad class of methods called successor features. And so successor features are assuming that I'm being given some state representation that is the basis set for all of the possible downstream reward functions that I care about. So this is the standard assumption that's made, is that this state representation is always linear with respect to rewards, downstream rewards. And then I can compute these cumulative state features, which look a lot like the successor measure. And so it turns out that it relates to successor measure through the following equation. Okay. And then I just need to minimize this objective in order to extract the optimal Z vector that gives me the optimal policy. And so FB, which we've seen a little bit before, is just a subclass of successor features that have a more specific parameterization. And so it divides up the successor measure into these forward and backward representations. So F captures the forward future occupancy according to some policy. And then I think B is supposed to capture some notion of backwards occupancy or information about how to reach S, I think. And so this is how I parameterize F and B. And so for FB, policy inference is actually quite nice because my optimal policy, as denoted by, as represented by this Z vector, has a closed form solution of just B times R. Proto-value functions. So the idea behind proto-value functions is that we're going to decompose value functions into a spectral basis. And so this is related to the Laplacian method that we also saw as a baseline previously. And so it turns out that the span of value functions using basis functions represents a smaller class of value functions than the set of value functions that can be represented using the span of the successor measure. And so that just means that if we fix the dimensionality that we're learning these basis sets in, that the successor measures basis set has more representational power compared to the basis set learned by proto-value functions. Okay. There's another perspective on self-supervised RL, which is about learning representations in exogenous block MDP setting. And so this set of this problem, we're assuming that our MDP has an exogenous process. There's some noise process that's happening, that's part of my observation, that's part of my state space that my agent can't control. And so then the problem becomes, can I isolate out and drop that exogenous process in order to construct a smaller MDP and solve that simpler problem? I want to learn a lossy compression of my state space. And so it turns out that you can actually do this by training a classifier that models the k-step inverse dynamics. And so from that k-step inverse dynamics classifier, we can actually extract a k-step successor measure of the behavior policy. And so we actually also have a method that does this. So rather than training a k-step inverse dynamics model, we just have a recursive method using a one-step inverse model. And so that's the connection between successor measure and controllable representations. And finally, we can also think about world models as a way of doing self-supervised RL. And so this encompasses learning single-step dynamics models, latent dynamics models. So that's what we did with RLDP. We can also think of generative models that predict future states or predict future several steps into the future as world models. And you can think of world models as a generative form of the successor measure. And so the policy inference step with world models would consist of planning with the model, just rolling out multiple trajectories and picking the one that leads to the highest reward. Okay. And so all of these nice results actually come from this RL unification paper that's currently in submission, but we also have this nice summary table showing how the components learned by all of these different perspectives connect to the successor measure. So we kind of already went over that. It also covers how we actually extract policies from these components that they learn. And then if we also think about the representations that you can extract from each of these methods, what do these representations capture? I guess like what states do they define as equivalent, right? So what states do they actually map to the same point in this latent representation space? That's also something that we show here. Okay, controllable representation. And then we have these sort of pros and cons of these different methods. So because they're all learning like different concepts, they're not exactly learning the successor measure. It turns out that how expensive policy inference is varies across these methods. What policies are actually easy to extract differs across all of these methods. And so we have this kind of pros and cons list. And so if you want to learn more, you can also look at the paper. So just to wrap up, I think self-supervised reinforcement learning is a very promising path forward in order to get RL methods to scale. If we think about this kind of pre-training and fine-tuning or pre-training and zero-shot policy extraction approach that has worked so well for LLMs, it seems like if we can design RL methods that can do the same, then we can open this up to robotics, to other kinds of sequential decision-making problems. We can apply these ideas to LLMs potentially and get, in order to improve the performance of LLMs and get better guarantees on what LLMs are capable of. And so I want us to focus on developing better approaches to approximate the successor measure. So the idea behind this unification of all of these different ideas of performing self-supervised reinforcement learning is that if they're all connected to successor measure, then we should all just focus on better ways of approximating and learning successor measure for some set of policies that we care about. And then that leads to a follow-up question, right? Should we use representations? Should we use generative models? What is the best way for us to represent this successor measure? And depending on that design decision of whether we're learning representations or generative models, that also changes how do we actually perform policy inference? What are we willing to pay in terms of how we learn the successor measure and how expensive is it to perform policy inference? And then finally, how do we actually restrict the space of reward functions or policies that we consider? There's no free lunch here, right? This pre-training approach that I'm describing is incredibly expensive, right? Because we're learning the optimal policy for every possible task, every possible reward function for an MVP. As we scale up our state action space, this is clearly infeasible. So how can we constrain the space of reward functions that we consider? And that's going to depend on the problem domain, on the application. And so I touched upon, let's see, 4 papers over the course of today's talk. And so this is work done by several folks in the group as well as other people in this room. And this is a pretty outdated photo of our lab, which doesn't include a lot of current members. And so I think we need to update this. But thank you very much for listening, and I'm happy to take any questions. Any question? Yeah.
I have another question regarding the policy class,
Yes.
because like you use this theory that you mentioned before to overcome the fact that this policy class might be infinite.
Mhm.
But like thinking about it, it seems like fundamentally there might be something else there, although it works in practice what you're doing, but it feels like there might be some assumption to make about the policy class that could lead to, let's say, because I assume in practice what you do is you use neural networks not to parameterize the policy, and then
Mhm.
just there's nothing to do there.
Yeah.
But what if you different parameterizations that can lead to, I don't know, some policy classes that are more structured somehow, like semi-linear, some sort of formal.
Yeah. So yeah. So actually all of these methods that I talked about, actually, yeah, okay. I think all of the methods that I've talked about are not making any assumptions about the type of function approximation used to represent the policy, right? Because the connection that we're showing is between the successor measure and the Q function. So really we're learning, we're trying to learn a structured Q function that allows us to, yeah, we're trying to learn a compression, like an optimal compression of the space of Q functions. But that looks very different from policies. And so there's nothing in here about actually compressing the policies.
Okay, so there's no way to say, okay, whatever task I might get can be approximated somehow by some form of, let's say, linear policy or.
Yeah, so none of the methods here actually have a closed form. Yeah, none of the methods here actually have a closed form solution for the policy. So you still have to perform policy extraction from the Q function. They only provide closed form solutions for all possible Q functions. Yeah, but that's an interesting setting that we haven't considered is how can we model this policy class? Any other questions?
I have a good question.
Yeah.
So, if you think of like, language models that are trained using PPO or whatever, right?
Yeah.
Then in your table, where is
Yeah.
it? Is that like a world model? Like, is an LLM a world model of language?
This is a
I'm
great,
trying
this
to
is a
map
great
between-
question.
Yeah,
Yeah, okay, so, yeah, LLMs are really interesting. I think the best way to think of it is the base model learned from the internet.
Yeah.
That is, you can think of it both as a dynamics model and a behavior policy, like a bad behavior policy, right?
Mhm.
But I can think of it as a dynamics model because any probabilities that are very low according to that model really represent infeasible dynamics, right? And so that's why I want to use that internet-based model as a dynamics model. My SFT model is now
it's a
supposed to
dynamics
be-
model. Is that the same as world model? Or is that a
Yes, yeah.
That is the same.
Yeah.
Okay.
Right, and so the dynamics model for an LLM really corresponds to, right, like grammar constraints, like logic, like physical world, like just, information like that,
Yeah,
right? Yeah. The SFT model, I can think of as like a better behavior policy. Yeah, I'll just leave it at that.
That's in effect giving the reward. So when you're doing SFT, that's communicating a reward function relatively cheaply after having built the world. So I think that's a good, that's a reasonable parallel.
Okay.
Because like in principle, like people could give any kind of feedback at the SFT stage, and it would quickly go to any number of policies that are consistent with the dynamics probabilities learned in the pre-training phase.
Yeah, yes, but you mean, using the context to specify the task.
Well, I was saying using the feedback that comes in the RLHF stage as the
Oh, as
proxy for the
reward.
reward function.
Yeah. But it means that there are potentially other types of approaches to improve upon SFT, right? Is which, I can, right, I probably just want to roll out trajectories according to my SFT policy in order to find improvements, but I could also use my base model. I guess I don't know why you would want to do that. It means you have more exploration compared to the SFT policy, but.
I mean, the base model tells you the sequences that you can get to
Yes,
with different probabilities.
yeah,
And then SFT is reweighting which of those sequences you want to go to.
yeah,
And that's very similar to the reward-free phase and then the reward-based phase. in
Yes.
this.
yeah. I guess my only point is that using the SFT policy to roll out trajectories is going to lead to a narrower search space according to whatever was good, like what the SFT data set defined as good. Right, and it depends on how varied your tasks are at evaluation time, and how varied your reward functions are, whether or not that's a good thing to do.
Okay.
Yeah.
Thanks. Let's thank the